Okay, great. Welcome to the video on exam 1 answer key. So I'm about to make an answer key for you for my exam 1. Question number 1, which atomic orbital combination would result in a sigma bond? First thing we can do is cross off A and D because those are to create pi bonds. Second, we can look, this would be constructive because the two white shaded orbitals are facing each other, whereas here we have one light and one dark. So this would not work. So the correct answer is B. The second question, how many hydrogen atoms are connected to the indicated carbon? We know that that's a carbocation. And remember that a carbocation is sp2 hybridized. It has a carbon with 3 things off of it and an empty p orbital. And so this would need to have 2 hydrogens. So the correct answer is C, 2. The third question, what is the correct Lewis dot structure for nitric acid, HNO3, including formal charges? And so if we look, we can get rid of this one immediately because nitrogen is going to be in the center of nitric acid. And if we keep moving forward, we see here that this nitrogen has an extended octet, which is not possible. And so we can get rid of number 1. And if we look at the 2 remaining, this species right here, the nitrogen would actually be positively charged, and this oxygen would also be positively charged, and that's not indicated. And so this would also not be correct. And on our final one, we have nitrogen, which is a positive charge. Oxygen up here is neutral, so that's good. This oxygen is negatively charged. And then we have the OH on the other side. So our answer for this question is number 4, the most feasible resonance structure. So which principle states that we can have a maximum of 2 electrons in any given orbital with the opposite spin? Remember, Aufbau principle has to do with the fact that we're going to fill the lowest energy orbitals first. Pauli exclusion principle says that we need 2 electrons of opposite spin in any orbital. Hund's rule says that we're going to half fill every orbital before we go back and completely fill it. That is any orbital of the same energy. Heisenberg uncertainty principle, you'll learn about that in P-Chem in your junior year. Le Chatelier's principle has to do with if stress is put on a chemical reaction that is in equilibrium, then the reaction will adjust. So the correct answer here is B, Pauli exclusion principle. If we look at question number 5, it says compare the bond length and strength of the following 2 compounds. This bond right here is a double bond. It has 1 sigma bond and 1 pi bond. This one right here is a triple bond. It has 1 sigma bond and 2 pi bonds. So this 1 and 2 is going to be shorter and stronger. And so the answer would be the shorter and stronger bond is found in 2. Number 6, which of the following is the correct resonance structure for A? The first thing I do in solving these problems is I put my electrons in. So my chlorine has all those electrons. So by definition, we cannot kick up into that chlorine because right now chlorine has an octet and it does not have the capability of an extended octet. So the only thing we can do is move these down and then hop up onto the carbon. So our correct resonance structure for this one is going to have a positive charge on the chlorine. So this one's wrong and this one's wrong. And it has to then have a negative charge on this carbon. So the positive charge will be on the chlorine, like right here, and the negative charge on the carbon. So the answer here is C. How many distinct p orbitals exist in the electron shell where n equals 2? Remember, we always had 1s and 3 p's. So the correct answer is B, 3. Okay, so we want to know how many sigma bonds and how many pi bonds are found in this molecule. And if we draw that molecule out, which is what I would highly recommend, we see that we have 1 H here, and then we have a C, and then this is a triple bond N. Now, many of you may not have known that that's a triple bond because many people got this question wrong and they picked D, and we'll talk about that in just a second. Whenever you are asked about bond angles or hybridization or sigma bonds or pi bonds or anything like that, it's in your best interest to go ahead and draw out the Lewis dot structure. So I think you can see here that we have 1, 2, 3, 4, 5, 6 sigma bonds. So it's either going to be B or D. And then we also have 1, 2, 3 pi bonds. And so that's going to be B is the correct answer. What is the electron configuration of phosphorus? It turns out the answer is C. So we have a total of 15 electrons in phosphorus in the ground state. And so this one adds up to 15, but it adds up to it in the right order. We have 1s2, then 2s2, 2p6, and then we have 3s2, 3p3. So C is the correct answer. Some of these are just in the wrong order or they're skipping orbitals. So the carbon-hydrogen bond in ethane, which is just CH3, single bonded to a CH3. So any one of these carbon-hydrogen bonds, we talked about polarity in terms of hydrogen and carbon being very, very close in electronegativity. And so it is essentially nonpolar. It's certainly not highly polar because that would be a very strong electronegativity difference like fluorine and carbon. It's certainly not ionic because we have two non-metals bonding to each other. It's not a multiple bond because carbon each can have 4 bonds and it's got 3 bonds to hydrogen already. So there's only one left to be between the two carbons. And then it's not resonance stabilized because there's no pi electrons or lone pair electrons to speak of. So the answer is going to be essentially nonpolar. The compound sodium methoxide looks like this, Na, and then we have O, CH3, and this oxygen has a negative charge and the sodium has a positive charge. And so right there you see is the ionic interaction, and then each one of these is going to be a covalent bond. And so the answer to this question is that it actually has a mixture of covalent and ionic. In the structure below, the hybridization of oxygen is what? And the COC bond angle is what? So the first thing I do for all of these is to draw in my lone pairs. Once I've drawn my lone pairs in on that oxygen, I can ask myself how many things are coming off of it, and remember lone pairs count. So we have 1, 2, 3, 4 things coming off that oxygen. So if I have 4 things coming off of it, it is going to be sp3. And then when I have 4 things coming off of any carbon, I use Vesper theory and figure out to make those get as far away from each other as possible. That would be tetrahedral, and so that's going to be 109.5. The 2 lone pairs actually push it down, so it's somewhat less than 109.5. So my answer here is D. Which of the following structures is another resonance structure for the molecule shown at the beginning? Now I look at this molecule and I see a lone pair next to a double bond. So I go ahead and kick this lone pair in and then kick that up, and that is in fact the way that this is going to happen. So we end up with answer B, where we have a double bond in between the nitrogen and the carbon, and then we have the electron pair pushed up. So we have a negative charge on the oxygen and a positive charge on the nitrogen. So that answer is B. In the molecule below, how many sp3 hybridized carbons are present? Remember, sp3 means that we have carbons with all single bonds, and so this is an sp3 hybridized carbon, this is an sp3 hybridized carbon, and this is an sp3 hybridized carbon. That is answer 3. If the question, however, was asking for sp2 hybridized carbons, we have 1 here, 1 here, 1 here, 1 here, and 1 here. And so that answer would be 5. But this question is asking for sp3, and that answer is shown in purple, and that is 3. What is the hybridization of the atom that's indicated in the molecule below? So we're looking at this carbon right here. How many groups are coming off of it? 1, 2. So we have 2 things coming off of it. So that would be sp. How many carbon atoms are present in the molecule shown? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The correct answer is C10. According to the pKa values listed for the set of acids, which would be the strongest conjugate base? Remember, a strong conjugate base equals a weak acid. And remember, a large pKa equals a weak acid. So this one right here is going to be the highest pKa, that's the weakest acid, and so its conjugate base is going to be strong. Because what that means is that the molecule would prefer to be in the acid form, and that if we pull that proton off, we end up having a very strong conjugate base, which would like to go back to that acid. Which proton is most acidic in the compound below? The protons that are on this carbon right here are very weak because they would make a negative carbon with no resonance. The protons that are on this carbon right here would be able to share its electron density with this oxygen, so that's good. So A is definitely stronger than C, but the H's that are on this carbon right here can delocalize into this oxygen and this oxygen, and so the B is going to be the most stable.
Conjugate base.
So the answer to this question, if I were to write it out, is proton B is the most strong acid because the conjugate base that's formed will be stabilized by resonance. Number 19, in the structure to the right, the sigma bond of the carbonyl is formed by overlap. So we're looking at the sigma bond that's right in between the carbon and the oxygen right here. So that sigma bond is the result of overlap of the oxygen orbitals and the carbon orbitals, and so they want to know what hybridized orbitals they are. So the oxygen up top has 1, 2, 3 things coming off of it, so that's going to be sp2, the oxygen, and if we erase that, the carbon right here has 1, 2, 3 things coming off of it, because that's also sp2. And so the answer is C, sp2, sp2, hybridized overlap on the sigma bond between the carbon and the oxygen. Question number 20, the frequency of stretching in IR spectroscopy depends on what 2 quantities? And so I said in the video that infrared depends on 2 atoms being at the end of a spring type mechanism where we have stretching and bending and twisting and wagging. If you remember the video, it has a lot of those animations in there. And so the 2 things that are really going to matter is how big and how heavy the atoms are and the stiffness of the bond. So if we have single bond, double bond, triple bond, and if we have heavy atoms out there. So the correct answer to this one is the masses of the atoms and the stiffness of the bond. C. Okay, so everybody got this question right. Oxygen has 6 valence electrons, so that's great. Number 22, what is the molecular formula of the line bond structure? So we have 1, 2, 3, 4, 5 carbons, so we're going to do C5, and then we want to know how many hydrogens, so there's 1 here, 1 here, 2 here, 2 here, and 2 here. And so we end up with a total of 1, 2, 3, 4, 5, 6, 7, 8. So we have H8, and then we have O. So the molecular formula for this compound is C5H8O. Okay, so how are we going to use curved arrows to show the movement of the electrons in the following chemical reaction? If we look at the starting material, we have nitrogen with 2 hydrogens, a lone pair, and a bond to a carbon. And then we have 2 carbons with a chlorine. And then we look at our final product and we have chlorine all by itself. So something is definitely going to happen with this bond. And then the nitrogen actually has 4 bonds now. So that lone pair is now a sigma bond, and the nitrogen has 4 bonds to it. So we had 2 hydrogens and a carbon here. We have 2 hydrogens and a carbon here. And so it has added to it this ethyl group, the CH2CH3. So let me erase all of those markings now that we know what we're looking for. We can erase all those markings so that we can actually now figure out how the bonds would move, okay? So the lone pair on the nitrogen reaches out and forms a new sigma bond with that carbon right there, and then the chlorine leaves. And so that gives us our nitrogen that is bonded to the 2 hydrogens and the carbon, and now also to this ethyl group that was right here, and our chlorine is by itself. So that is the answer to that question. 24, indicate all the non-zero formal charges in the structure below. This oxygen has 3 lone pairs and a bond, and so that's negative. This nitrogen has 4 bonds, and so that's positive. This carbon right here has 4 bonds, and so that's good. This oxygen has 2 bonds and 2 lone pairs, which is good. This carbon has 4 bonds, and so we are good. So that is a negative charge on the oxygen, a positive charge on the nitrogen. If we draw the line bond structure for that molecule right there, we see that we have 1, 2, 3 carbons in our main chain, and then off of this carbon is 2 methyl groups, 2 of them. So we do 1, 2, And then off of this carbon is 2 hydrogens, which we don't draw in this case, but we do also have a nitrogen off of this, and we have to draw our hydrogens off the heteroatoms. So now a way to verify that we've done this right, because several of you got this part wrong, is how many carbons? We have 1, 2, 3, 4, 5. So we have 1, 2, 3, 4, 5. So that one's good, and we have NH2, and so that is the answer. That is the line bond structure for that molecule. If we add the formal charges to this molecule, remember nitrogen, in order to be neutral, needs 3 bonds and a lone pair, so this one right here is good. The next one over is a positive charge because it has 4 bonds, and the next one over is a negative charge because it has 2 bonds and 2 lone pairs. Remember, nitrogen is in group 5, so if you take the group number 5 and you subtract from it the number of things right around it, that's 4. So the first nitrogen is positive. Nitrogen is in group 5, and you subtract the electrons right around it, and that second one is 6, and so this is going to be -1. So this is +1, and this is -1. If you look at the next acid-base reaction, we have to predict the products. I would immediately realize that this is going to be my base, so that's the proton acceptor, and this is going to be my acid, my proton donor. And so we have our negative base reaching out and picking up that proton. So our answers will be CH3, 3N with the lone pair on it, plus H2O. Okay, and the next one, same thing. We're going to look at the acid-base reaction, and we need to identify the acid and the conjugate acid. So if you look at the starting materials, we have NH3, and over here we have NH2. So this guy right here donates a proton. And then here we have H minus, and we have H2, so that one gained. So a proton donor is going to be my acid. This would be my base. And then over here, going back, this is acting as my conjugate base because it's what's left after I donate a proton from this, right? So that's what's left. That's a conjugate base. And then the conjugate acid is the thing that would donate a proton on the reverse reaction. And so this is going to be my conjugate acid. Question number 29, why is the pKa of acetylene 25 while ethene is 44? Okay, so first of all, telling me which one's the stronger acid does not answer the question. This is asking why. But to start answering why, we can indicate that the C triple bond C is a stronger acid than the C double bond C H. The H on the alkyne is a stronger acid than the H on the alkene. Okay, the question though is asking why. So many of you wrote smaller pKa, so it's a stronger acid, and you thought you answered the question, but this question is asking why. So the correct answer to this question would be that acetylene is a stronger acid because the conjugate base is more stable because, and then you can either say it has more S character, or you can say because the electrons in the conjugate base are closer to the nucleus. You can say because the orbital is smaller, it's shorter, and so it's held closer. So there's a lot of different ways you can explain it, but you need to state why is it a stronger acid? It is a stronger acid because the conjugate base is more stable, because the orbital has more S character, and the electrons are held closer to the nucleus. Now, if we were going to draw curved arrows indicating this one resonance structure going to the second resonance structure, we have to start where the molecule is negative and move in. So we take the lone pair that's on this carbon, kick it into this bond, this goes over to this bond, and then this goes up onto the oxygen. This is the correct answer. The way the arrows are shown here, don't worry, I will go back and I will tell you the right way again. But so many people had this bond go here and this bond go here. So what is wrong with this arrow pushing? First of all, our oxygen now does not have an octet. And to date, we have not talked about oxygen not having an octet. I've never shown you that, and I won't. We said carbon cannot have an octet as a carbocation, but that's really an exception. And what else is wrong with it? This carbon right here has 2 hydrogens on it and a lone pair. And so now you have just made carbon have an extended octet. And so there's multiple things wrong with the way this goes. That oxygen would look like this with 2 lone pairs and 1 bond, so it doesn't have an octet. And then we have a double bond here, a single bond here, a double bond here, and then we have a single bond, and then we have 2 H's and a lone pair. So that's crazy. So let me erase all of that and I'll put the right answer back. Whenever we talk about resonance structures, we have to go back to those patterns that we learned. A lone pair allylic to a double bond will kick in, and then this can kick over, and then this can kick up. This is what's going to give us a double bond here, and then a negative charge on the oxygen. So sometimes it's going to be important to look at the product before we go ahead and start drawing arrows. Okay, Lewis dot structure for CH2O2. So carbon goes in the middle, and it's going to be bonded to 2 oxygens and a hydrogen. We know that one of those oxygens is going to have to be double bonded, and so that is the Lewis dot structure for that formula. NaCl is an ionic compound. Hexane is very nonpolar, so it will not be soluble. Okay, so this one I think is probably the hardest question on the test. We have a CH2 next to a CH3, and we have an anion there. If you want to redraw that species, that lone pair is going to reach out and form a new sigma bond with that proton, and then the 2 electrons in this bond are going to hop onto the end of that triple bond. And so ultimately we have CH3. CH3 is one of our products. That's this one. And then if we look at this one, we have this, and then we have a triple bond. And now we've taken that sigma bond and moved it as a lone pair on the end. So we have conservation of charge. Oh, sorry, I just can also draw the MgBr. That's just a counter ion, maybe like a spectator ion that hangs out near negative charges to help it kind of be stabilized. So we have a negative charge and a positive charge, and so that's what we have in our product. We've now created ethane, which is just CH3CH3, and then we put that negative charge onto the end of the alkyne. Rank the following compounds in order of increasing acidity. So that means we're going to do the weakest acid first. So this species right here is the weakest. So we're going to call that 1. And then I recognize this one very quickly as being the strongest because it's got 2 fluorines on that, lots of electron withdrawing, lots of inductive effect. And so if we need to, we can go ahead and draw the conjugate base of each of these, although at this point, I'm just going to have to do one because they're very similar. So if we draw the conjugate base of that, we can talk about now, this is the strongest acid because the conjugate base is stable, not just because of resonance, because they all have the resonance. They all can delocalize. So those are equal. But the reason this one is more stable than the rest is because of inductive effect. So fluorine is most electronegative, and so it will have the strongest plus its closest. Okay, so the conjugate base of this one right here is more stable because of the inductive effect, because fluorine is the most electronegative and is the closest. So next after that one, so we can call that number 4, right? That's our strongest acid, and so that's going to be at the end. So if we look at the chlorine, which is 2 away, and the bromine, which is 3 away, then bromine comes next in terms of being the second weakest, and then chlorine is going to be the second strongest. So the final answer for this question would be that the order is that we have the weakest one with no electron withdrawing group, moving all the way up to the strongest one with 2 very highly electronegative atoms. So my answer would be, I have ranked these acids and bases in order of increasing activity. The strongest acid is the strongest because its conjugate base is stabilized by the inductive effect of the 2 fluorine groups being highly electronegative, close to where the conjugate base negative charge is developing. That is followed by the chlorine, which is 2 away and also highly electronegative, the bromine, which is 3 away, still pretty electronegative, followed by the weakest acid, which has no inductive effect and no stabilizing of the conjugate base inductively. Okay, question number 35 is a little twist. We want to put them in order of increasing basicity. And so the weakest conjugate base, and many of you had the order correct. The weakest conjugate base is this one, followed by this one, followed by this one. And so if we were to describe why, which it says, explain your rationale. So this is the weakest conjugate base, this is the middle one, and this is the strongest. And so the reason that this is the weakest compared to this is that this one has resonance. So the conjugate base is stabilized by resonance, which makes it a weaker base. And then if we talk about why these two are different, this one is going to be a stronger base compared to this one. And we can say that that is because of the atom. So the oxygen prefers the negative charge. So the oxygen is more stable of a conjugate base, making it weaker, because oxygen can handle a negative charge better than nitrogen. And so the reason between these two is resonance, and the reason between these two is atom. Going back to our ARIO. So on this molecule, we're drawing the resonance structures. And so the first thing I do is I put my double-headed arrow, and I recognize right away that we have two different patterns that we see. We see a lone pair right next to a carbocation in one pattern, and we see an allylic carbocation in another pattern. First of all, we take the lone pair on the nitrogen, and we kick that in to form a double bond here. So our first resonance structure will look like this, with a positive charge on the nitrogen. Our second resonance structure, if we can go back to our original and talk about moving the two electrons from the pi bond and to form a double bond there, our second structure is going to leave the nitrogen the same as the original, and then we have that, and then we have a double bond here, and then we have a positive charge out here. To be completely correct for resonance structures, this needs to be in a box. We need the double-headed arrows here, and then finally we need to circle the major contributor of the overall resonance hybrid. So the major contributor between this one, and this one, we have a carbocation here, we have a carbocation here. Those don't have filled octets, and that's the first rule. This one in the center has all filled octets. Positive charge on the nitrogen, which we can handle because all of the octets are filled. So this is our answer. Number 37, a lot of people got wrong, which I'm confused about because we did do this one as a question of the day in class. I hope and I think most people understood when we circle the weakest acid that it's going to be this one right here. It's the weakest acid because its conjugate base does not have any resonance. Now, when we talk about 1 versus 3, which one is the strongest acid? It turns out it's this one over here. Yes, I agree that number 3 does have resonance structures, but in those resonance structures, the carbon atoms are negative. But in this resonance structure over here, even though there's less resonance structures, the negative charge is on the oxygen, both cases. The answer to this question is that number 1 is the strongest acid and number 2 is the weakest acid. And the reason is that the conjugate base of number 1 has resonance structures where the negative charge is on the most electronegative atom. 2 is the weakest because its conjugate base does not have any resonance structures. And 3 is in between those two because although it does have resonance structures, the carbon does not like the negative charge as much because it's not such an electronegative atom. Question number 38. So this right here is an alcohol peak, so that's OH. These right here are going to be sp2 hybridized CH stretches, so double bonds. These right here are sp3 hybridized CH stretches, which are going to be single bonds. Up here we see the aromatic saw shape. So we know that we have an aromatic compound, which just means conjugated, which just means we have benzene with an alcohol, okay? So we can get rid of this one, and so we can get rid of this one because there's no OH, and we can get rid of this one because there's no OH. So the big question now comes down to, is it the first or the third? Now, I don't know if you remember this or not, but when we have a carbonyl on a compound, we are going to see a very strong peak right around 1700 wave numbers, and we do not see that peak. And so it cannot be this compound. So the correct answer is the first one. And so let's take a look at 4 functional groups that are in Tamiflu. Right here we have an ether. Right here we have an amide. Right here we have an amine. Here we have an ester. I only asked you to find 4, but there are 5 here, and this is an alkene. C3H8O, we have to figure out all the different ways we can put those atoms together. and make 3 constitutional isomers. So that's our C3, and we can add an alcohol here. We can add an alcohol here, or it turns out we can make an ether and do that. And so these are the 3 different ways that we can put these atoms together to make compounds. So here we have an alcohol, and an ether. And so that's the answer to the first part of the question, the 3 compounds with the molecular formula C3H8O. Now, if we talk about boiling point, this one right here is going to have the highest boiling point. That is because it is both linear, flat, and hydrogen bonding. So we have stackability and H bonding. Now, in our center alcohol, we definitely have H bonding. So that is going to come in second in terms of boiling point. But because it's got branching, that's going to have a little bit less of the London dispersion forces. And then over here, with no OH, so there's no hydrogen bonding, over here we just have dipole, dipole. And we know that that's a smaller interaction than hydrogen bonding. So it goes 1, 2, 3. And if I summarize real quickly, number 1 has hydrogen bonding, dipole, dipole, and maximum London dispersion. Number 2 has hydrogen bonding, dipole, dipole, and a little bit less of the London dispersion. And number 3 has dipole, dipole, and London dispersion, and it lacks hydrogen bonding. So the boiling point would be ranked 1 for the linear alcohol, 2 for the branched alcohol, and then 3 for the ether.